Hey, good morning, everyone. I see the numbers are dwindling. It's getting towards the end of the semester. So the people that watch the recording, if you get low marks on the midterms or the finals, maybe you need to come to class. Everyone here is a straight A student, yeah? Okay. But you guys should come to class. Okay. This is why I didn't put the recordings up at the start of the semester. Everyone's like, why didn't you put the recordings up straight away? And do that, half the class doesn't show up. Okay. Today we are moving on to pretty much the final topic, or the final major topic within a little subsection at the end of this course about discrete mathematics. And we are talking about graphs. So just a few examples here of graphs in the real world. You guys are no doubt familiar with the SkyTrain map. Things like tube maps or subway maps are often represented in graph form. And in the pre-lecture, it talked about vertices and edges. So in the case of something like a SkyTrain map, our vertices are our stations and our edges are the lines connecting those stations, right? So you guys have been meeting graphs without even realizing it. The reason we use this kind of representation is because we care about the relationship between the stations and between the lines. We don't really care about the other details in terms of the geography or the distances between these things. There's lots of famous examples in the London tube map. Has anyone been to London? Probably not London, not London, Ontario. Okay, so yeah, that looks like a mess, just like with all of these lines sort of drawn all over. There's like a famous thing, I can't remember the two stations, but there's two stations in London that look really far away on the map or really difficult to get to, but they're actually just a very short walk away. So these representations, when we put them in graph form, tell you something about the relationship between, say, edges and stations. So the lines of tracks and the stations that they connect to, but they don't necessarily represent accurate distances in the real world. Okay, so what other examples do we have? You guys have probably met phylogenies or at least seen them somewhere before. Hands up if something like this looks familiar, tree of life. Okay, great. These are graphs, okay? They don't look maybe quite like graphs here, but we can think about these as having the tips of these graphs as also being vertices and the internal branching points as vertices as well. Here, this is known as a tree. A tree is a specific type of graph. We're not going to be talking about trees, but there is another course that we're currently developing. I think it'll be a 400 level course maybe that will talk about discrete mathematics in the context of trees and graphs and what that means for mathematical biology. These are used extensively, including in epidemiology. So this is a phylogeny or SARS-CoV-2 caused the pandemic. So we can use these tools from graph theory to understand a wide range of problems, whether it's understanding tree of life, whether it's understanding things like transport maps, and also things like infectious diseases. Okay, so just to summarize what the pre-lecture was about. So we had this introduction to quite a bit of different terminology related to graphs. So some of these things are just things to take on board in terms of definitions. So we have this idea of vertices or nodes. I might use those terms interchangeably. These can represent anything from people to stations to some objects, something more abstract potentially. And then we have edges between those vertices. And we can define a vertex set. So that's the set of all vertices, and an edge set, a set of all edges. And then we can write a graph G is equal to the combination of these two things, our vertices and our set of edges. Other terminologies that are important to remember: loops, they are what they sound like. That's a loop, an edge that joins a vertex to itself. Parallel edges occur when you have two vertices that are joined together by two or more edges. So these edges here are parallel. That would be like having two stations where you could go between those two stations with no stations between them. And there's two routes that you could get there. Okay, so a green line and a red line or something like that. Isolated vertices, again, they're what they sound like. They're vertices that have no connections whatsoever. Okay, the next thing in terms of terminology is the degree. So we say that the degree of a vertex is just the sum of all the edges that are joined to that vertex. So we say incident just means joined to that vertex. So in the case of V1 here, we've got one edge, two edge, three edges, and four edges. We count that loop twice because it's joined to the vertex twice. Okay, this, if I take another example, V6 has this edge here, and this edge here, so it has degree 3. So we end up with this relationship that if we sum up the degree of every vertex in our graph, that's equal to 2 times by the number of edges. Okay, so remember, capital E was our edge set. This, these bars either side of it are just saying the size of that edge set. So in other words, the number of edges in my graph. So why does that make sense? Well, if we have an edge, it must connect either to the same vertex or 2 different vertices. And so that edge is going to add 1 to each of those 2 vertices or 2 to the same vertex in this case where we have a loop. So that's why that holds. The next thing is paths and connectedness. So paths are what they sound like. A lot of the time with our graphs, the terminologies are fairly intuitive. So path is just some set of instructions, if you like, leading you from one vertex to another along certain edges. So for example, V3, V4, V2, V10, V6, V8, V5, that is a path. And if a path exists between 2 vertices, any 2 vertices in our graph, then that graph is connected. We can also have open paths or closed path. That was an example of an open path here. If I was to follow V5 along E7, back to V3, I have a closed path. A closed path is one where the start and the end nodes are the same. So like I said, a connected graph is one where we can take any 2 vertices in that graph and we can draw a path between them. So in this case, G2 here is connected. I can choose any 2 nodes or vertices here and find a path between them. I can't do that in G1. It's disconnected because there's no path that exists between V4 and any other vertex here. Okay, the last and really important thing here is directed graphs. We're going to be talking a lot about directed graphs when we talk about food webs next week. Food webs use these directed graphs because they are telling us about the flow of energy through a particular ecosystem. So directed graphs are related to our underlying graphs. So this here is an underlying graph. It has no arrows on it. There's no direction to these edges. We just say V1 and V2 are connected by edge 1 here. In this case here, the digraph or directed graph above it is an arrow pointing from V1 to V2. So that's saying essentially that you can only travel in that direction. Okay, so you can think of the arrows as being like one-way streets. You can't go from V2 to V1 like this, but you can go from V1 to V2 like this because that's a one-way street pointed in that direction. So when we have a directed graph, rather than talk about the degree of a vertex, we can talk about the in degree, or indeg, and out degree, outdeg. Okay, so obviously if we sum up the in degree and the out degree, we're going to get the total degree. In degree is just all the arrows pointing in, the out degree is all the arrows pointing out. So we just count those things up. Okay, that's a summary of the pre-lecture material. Any questions on intro to graphs before we move on? Nope. Okay, let's do some problems. Okay, so here we've got an example of a graph. I just want to run through here to make sure that what I just said was clear. What are these different concepts? So our vertex set here is just going to be our vertices V1, V2, V3, and so on up to, how many have we got here? 9, I think. Should be 9. And our edge set is likewise just going to be V1, V2, and so on, all the way up to V12. Nice and straightforward. Can anyone tell me, can anyone identify loops? Yeah. Yeah, so E1 and E8 are loops. this one here, and this one here. Remember, a loop is just an edge that joins a vertex to itself. How about a parallel edge? Can anyone identify, well, there'll be two edges that are parallel. Yep. E10 and E12. So let's have a look. Yes. E10 is this one here. I zoom in. That's that one. And E12 is this one here, curved. Okay. So they're parallel because they both join V8 and V9 together. So E10 and E12 are parallel. Isolated vertices, anyone? Someone different who doesn't normally answer. V3. See, nice and straightforward, right? Okay, degree 0 vertices. So remind me, someone tell me what the degree means. Exactly. So V3. So an isolated vertex has degree 0 by definition. It has no edges joining it. That's what makes it isolated. How about degree 1 vertices? Not V6. So V6 has, it's got one edge, but it's got that edge joining itself. So we count that twice. So V6 is actually, I'll put it down as a degree 2 there. V4, yes. Just checking I haven't made a mistake, missed any. Yeah, V4 is the only degree 1 vertex here. Degree 2 vertices. So we've already got V6. Are there any others? So V9 has 3 things coming out of it, and V1 has 4. So we'll put V1 as 4, V9 as 3. Don't think there are any other, no, there aren't any other V2 vertices, degree 2 vertices here. Degree 3. So V2. So where's V2 here? So degree 3, yeah, V3. Sorry, V2 has 3 edges going out of it. So we've got V2 here. There's one other, I think. V8 is, let me find V8, there we go. 1, 2, 3. Perfect. And then degree 4 vertices, we've already got V1. Can anyone else identify any others? 7. So someone said V5 and someone said V7. So V5, 1, 2, 3, 4. Yep. And V7, 1, 2, 3, 4. Yep. I think that's it for V degree 4. Okay. Closed paths and open paths. An example of a closed path is one, say, go V1, down here to E2 to V2, then along here from E5 to V5, and then up here back to V1. That's an example of one. If I was to write this out, it would be V1, E2, V2, E5, V5, E3, V1. An open path would be similar, but just not joining the last things there. So an open path could be, for example, just that bit there. Note that we have to always have vertices at the beginning and end of our paths. We can't end on an edge because the edge has to connect to something. Okay, that would be like, again, to use the train analogy, you'd be going from one station along a line, but you wouldn't be ending at a station. You always have to end at a station. Okay, yeah. Sorry? As in a path without any edges. That's an interesting one. So basically is just V3 a path? Good question. I'd have to look that up to make sure it is, whether it is technically a path. There's probably like a definition somewhere that says that it has to contain paths and edges, but in theory, you could just say it's a path of length 0. Maybe. I have to look up the definition as to see what it exactly is, but good question. Okay, so closed path, open path are very closely related. A circuit, this also happens to actually be a circuit here. A circuit is a closed path where we have no edge used more than once. So there's no reason why when we're following a path, why we can't do it in a different color. There's no reason why we can't go back and forth over the same thing. So I could do V7 to V9 along these edges here, and I could just keep going back and forth, right? It's still a path, but that's not going to be that's not going to be a circuit because I'm going back and forth over the same edges, okay? So if we don't use the same edges, so if I give an example of a path here, so if we go from V7 down to V8, down to V9 this way, back via E12, and then along E9 again in this kind of lollipop-like circuit path here, that's not a circuit because I've used E9 twice. But if instead I went from V7 down E9, down E10, and then back along E11, I've not reused any edges, so that is a circuit, okay? Right, I'm going to get you guys to have a go at this one. So a simple graph, we're going to draw all the simple graphs that are possible when we have just 4 vertices, okay? A simple graph is one that doesn't have any loops. So we know what a loop is. It's where you've got a vertex that joins to itself and parallel edges. So a simple graph doesn't have loops or parallel edges. A parallel edge will look something like this, okay? So have a go at drawing all possible simple graphs. Work through the number of vertices. So think of, the number of edges, okay? So if we have the first case, there are 0 edges in this graph here, 0 edges. Then think about 1 edge, 2 edge, 3 edge, 4. The key thing about these graphs, just before you do that, is because the spatial relationship between these things, how we actually draw them on the page, the location that we put our vertices, and how we actually draw those edges, whether they're curves or lines, that doesn't matter. We can say that they're topologically the same. So what I mean by that is this graph here, if I say draw it with 1 edge here, that is the same as this graph here, okay? Because I could just rotate everything around. We're not caring in this case about the labels between these vertices. These are unlabeled. So all I want you to do is draw all possible relationships that we can have between these vertices with different numbers of edges. So go through 0, 1, 2, 3, 4, 5, and 6 edges. See what you guys come up with, okay? Remember, if you can do something like that, if you can rotate them or just switch the order around, it's not a different graph, okay? Have a go at doing that. Chat to your neighbor and see if you guys can come up with all the options. Okay, let's see how you guys got on. This is more of a fun exercise rather than something that I would ask you to do on an exam, but it's a good way of thinking about the relationship between the vertices and edges, okay? Okay, so there's only one example where we have 0 edges here. How about 1 edge? So I'm going to just draw these all in the same orientation in terms of having my vertices like this. There's nothing special about this. You could have done them like this, or you could do them in a line. It's entirely up to you. Okay, so there's only one way in which we can have 1 edge. Okay, so I'm just going to draw it between these two here. If I drew, say, this one as well, I don't know if I can rotate here. I hope I can. Can I rotate? No, I can't. That's a shame. This one here would be just the same if I flipped it round. So let me get this back. If I can interchange my vertices, or I can do some sort of movement on the page, because the position on the page of my vertices doesn't matter, if I rotate this one here around 90 degrees, I'll get the same graph, okay? So that's why there's only one unique way that we can join up these vertices with 1 edge. That would be the same thing, right? We can, because the position on the page doesn't matter. Sorry, I don't know who asked. There was a voice from the dark over there. Okay. So if I switch the order of these two here, you can think of these as being a little bit like, in this case, pegs that are in the ground, like in the sand, and they've got ropes between them. And you can pick up a peg and you can put it anywhere else you want, okay? The rope is still connected to it, and you can walk around those pegs that are on the ground. So it doesn't matter which way I'm looking at it. We want to get different things, basically. So we class a graph as being different in this case. If in the pegs and ropes example here, if you can't sort of just walk around and get a different orientation, you can't pick them up and place them down and get the other graph, okay? You'd have to do something like taking one of your connections, one of your ropes away. You'd have to untie it and tie it to a different peg, okay, to get that graph. And that becomes a bit clearer when we have more edges. Okay, you had a question, yeah. Yes, exactly. If these were labeled V1, V2, V3, V4, and so on, then it wouldn't be the same to have a link between these two, say V1 and V4. Okay. Okay, two edges. This is where it starts to get a little bit more interesting. So this is an example of one with two edges. There's only one other case, which I'll draw like this. Okay, so why are these different? Well, we can think about the degree of these vertices as one indication as to why they're different, right? So this graph has a vertex of degree 2, and it has two vertices of degree 1. So 2, 1, 1 other degrees. It also has one of degree 0. This graph on the right-hand side, every vertex has degree 1. So there's no way that I can pick up those pegs and move them around in the second case here to get a graph or a vertex that has degree 2, okay? Because I can't untie those ropes and tie them to a different one. That's not allowed, but I can pick up the pegs and move them around, okay? So there's no way that I can go between these two graphs without untying one of those ropes and tying it to a different peg, okay? Someone had their hand up over there, I think. Yeah. So if you make an X shape, let's draw that out. So an X shape like this, if you think what happens if you pick up, let's highlight it, if you pick up this peg and switch them over, you'll be back into this scenario here. Okay, so you can pick pegs up and move them any way you want to, but you can't untie the ropes attached to those pegs. So there are only two ways in which we can make these graphs. So looking at the degree is a good way of indicating whether you can move between them. If you look at the degree of each of these vertices, the degrees cannot change. Okay, three edges, a bit more complicated again. So how many different ways can we do this? Turns out there are three ways that we can do this. One way is like this, so where one of our vertices is connected to all the others. So note here we have one vertex with degree 3. We could have something that looks like this. Note these two, we can't just pick up the pegs and move them around to get the other one, because the second graph here does not have any vertices with degree 3. So these are definitely different. And then the only other case we can have is something like this, where one of our vertices has degree 0. Who got those three? Cool. Done. Okay, degree 4, or rather 4 edges, not degree 4. In this case, there are only 2. What do these look like? Well, this one's nice and straightforward. If we just draw a square, every vertex has degree 2. If we untie, say, this edge, and we tie it to another peg, like this, then we get a graph that looks like this. This is the only other simple graph that we can have. There are 2 options here. 5. So if we start with our square here, we can draw one other link, say like this. There's only one way in which we can do this. Again, you can pick them up and move them around. There's only one way you can get 5 edges. And 6 edges, there's only one way in which you can do 6 edges. Does anyone notice any patterns here? There was one way to do this and one way to do this. One way to do this one way to do this one. 2 ways to do this one, 2 ways to do this one. Symmetric. This is linked to things like counting, the number of ways in which we can do things. Okay. Yes.
Why is it the example where line where the two
so 2 diagonals and then 2 straight, say like this and this. Okay, so if I pick up this peg and this peg and I change the order of them, I'll get this. Yes. Yes. So a loop is where we have a vertex connected to itself. And a parallel edge is where 2 vertices are connected by 2 edges. Okay, that's a good question. Any other questions? Yes. This one?
Yeah. From the top right to the bottom right?
From the top, as in take this peg and put it here.
Below that one.
Oh, sorry. Top right to bottom right.
Yeah.
Yeah, so you'd have something that looks like the same, as in, do you mean the same as this?
Yeah.
No, because in this case, if you exchange the location of those, you'll have something that looks like this. Remember, what we can do is we can move those pegs that have the ropes attached between them, but we can't untie the pegs. So if we look at the degree of these vertices, so in this one on the left-hand side, this has degree 2, this has degree 2, this has degree 3, this has degree 1. Okay. If we look at the one on the right-hand side, this has degree 2, this has degree 2, this has degree 2, this has degree 2. So the only way I'd be able to go from this one to this one is untying one of those ropes and tying it to a different peg. Because otherwise we can't, they've all got degree 2, so that means they've all got 2 ropes attached to them. Whereas the one on the left-hand side, one of the pegs has got 3 ropes attached to it, and one of the pegs has got 1 rope attached to it. Okay. Okay, I'm going to move on from this just because there are obviously lots of different ways in which we can think about, is this a graph or not that graph? I think it's a good exercise to think about. I'm probably not going to quiz you on this on an exam. It's just to get you guys thinking about the interchangeability and the fact that the location of these vertices doesn't matter on the page. Okay. Okay, I'm going to skip that question. I might come back to it. I'm going to go to this one at the end, actually, here, because it's a more applied one. Any NBA fans? Yeah, okay. So NBA has 30 teams, and they play 82 games in a season. Okay, the association is broken into 6 evenly sized divisions. Can anyone tell me how many teams in a division? Okay. 30 divided by 6 is 5. Well done. University mathematics at its finest. Teams play members of their own division the most, okay, for reasons of rivalry and limiting travel. Question here is it possible for each team to play exactly half of its games within its own division? Okay, so this is like scheduling nightmare for the people that have come up with this. How do we divide up the number of games between that occur within a division, within a conference, and between conferences? It's a little bit tricky, but we can use what we know about graphs to understand this problem. Okay, so how do we do this? Well, as you guys have just calculated, there are 5 teams in each division. You think of these as just being team 1, team 2, team 3, team 4, team 5. So we're just going to consider this one division. And we can think about just that graph by itself, okay? Ignore the other games outside of this division. We want to know, is it possible for each team to play exactly half of its games within its own division? So what does that look like as a graph? So we have these 5 teams. And they're going to have lots of edges coming out of them. And we're just going to be concerned with what goes on within this division. Okay, so they're going to be playing each other over and over and over again. There's only 5 teams here. We want them to play each other lots of times. We want half of their games to be within the division. So we're going to have lots of parallel edges here. I'm not going to draw this here because 82 games, half of them for each team. Every vertex is going to have degree 41. Okay, so I'm not going to draw 41 edges coming out of every one of these. So the degree of any team TI in this graph is going to be 82 over 2. So it's 82 games, and we want half of them to be within the division. That's 41. Okay. What happens then if we add these up? Take the degree of all of these teams from 1 to 5, add them up. It's going to be 5 times by 41, which is 205. So, is it possible to have a graph with 5 vertices and 205, or rather a total degree of 205? Is that possible? Remember we had this in the pre-lecture? We had this relationship here. The sum of the degree is equal to what? Can anyone remember? 2 times by the number of edges. So, does that help you at all to figure out whether we can have each of these teams playing half of their games within the division? What do we know? The sum of the degree, if they do play half of all their games within this division, is going to be 205. And what do we know generally about the sum of the degree? The sum of the degree has to be 2 times the number of edges. So how many edges would there have to be? Say it a bit louder.
Not a good number.
Not a good number. Okay. Anyone else? Not a good number? Why is it not a good number? Yeah, so you'd have 102.5 edges. We can't have half an edge. It's not possible. You have half a game. You could have half a game in theory. So it's not possible. Okay. So it's a nice little simple way of understanding quite a complex problem here of how do we do this scheduling? You can say, well, we can't have this, we can't have each team within this division playing half of its games within the division because we know that we need to have 2 times by the number of edges, but the number of edges is going to be, or 2 times the number of edges here would have to be an odd number. Yes. So it will depend on so I'll leave that as an exercise. What happens if you have 4 teams or 6 teams? So you can go through the same principle there, or if you change the number of games, right? To change the total number of games. So have a think about those different, how if you structure this problem slightly differently, could you come up with a scenario where the teams can play half of their own games in the division? Okay. Cool. Let's think about another slightly abstract problem here. Okay. let's think about what happens if we've got the general connected graph. Remember, we can just say our graph is given by this notation here, our vertex set and our edge set. Explain why the number of edges is always greater than or equal to the number of vertices minus 1 when we have a connected graph. Okay, so let's think about what a connected graph looks like. I'm just going to draw any old graph. And it's connected, so that means that we need to be able to find a path between any two vertices in this graph. So this graph here is connected. If I'd had some other vertices over here, this could still be classed as, this is still a graph, okay? But it's not connected because I can't say, find a path between this vertex and this one here, okay? So it's disconnected. So we're interested in just connected graphs, like the one on the left. Okay, so this is going to be a connected graph. What I'm going to do is I'm going to remove any edge that's on a cycle. So a cycle is where we are going from, say, here, down an edge, and then following a path that leads us back to that edge again. So we can just go through and start eliminating some of these. So I'm going to get rid of this one here, and this one here. And basically, we're just removing edges while still leaving us with a connected graph, okay? And we're going to remove as many of them as we can. So let's also get rid of this one here and this one here. So what does that look like now? I draw this out again. There's an edge there. Sorry, I meant to draw one on there. I'm trying to keep things identical to the notes that I've got here. There should have been one there. Was that why you had a look? Someone had a look of confusion then when I removed something. We have these ones here and these ones here. So this is still a connected graph, but I can't remove any more edges at this point, right? If I remove any of these edges, it's going to be a disconnected graph. So if I take this one out here, this vertex here is going to have degree 0. So what we're doing is we're just taking these away. Again, you can think of these as pegs with ropes between them. We want to do that to the point where there's no, that we still have there's still a path, there's still a rope linkage between all of the pegs. We don't have a disconnected graph. So what happens if we do this? Well, if we do this, we can count up the number of vertices, 1, 2, 3, 4, 5, 6, 7, 8 in this case. So V is equal to 8. The size of V is equal to 8. Number of edges, 1, 2, 3, 4, 5, 6, 7. So clearly, if I call this a general graph G and this T here, this is a tree. I mentioned trees at the start. That's why I'm using a T here. To reduce a connected graph down to a tree, we can see that the number of edges here is equal to the number of vertices minus 1. So that's true for a tree. And we can take, remember that tree we obtained by just removing edges from our graph G. So for a general graph G, this is always going to be greater than or equal to the number of vertices minus 1. Okay, because all I'm doing, if you like going back in the other direction, to get G, I'm adding edges in. I'm adding these edges in to get back to G. So the number of edges here on this left-hand side has to be increasing. Okay, so that's why if we've got a connected graph, the number of edges always has to be greater than or equal to the number of vertices minus 1. Okay, it's 3 minutes left, so I'm not going to go through any more questions. Have a good weekend. One more week of actual material to do. The last week, I'm going to go through reviews on the Monday and the Wednesday. So think of anything that you want me to go through and let me know.